So a big picture of what we are going to talk about today and also for the following weeks. So we may need one lecture for the overall design of the ADC, and we need another lecture on Friday for digital design models, so you understand all the parasitics of the capacitors. And starting from the week after the spring break, we'll start working on some hands-on stuff. I don't know, there will be so we have to cover memories, RAMs, but after that, I think I'm gonna give the time to you guys, and during the lecture time, we'll probably work in the lab to do all the cadence tutorials. Okay, you can see that on the schedule after spring break, it's gonna be mainly just hands-on. And the reason I really wanted you guys to spend a lot of time on that is because if you look at this one, so one of the senior SAMs we did a few years ago, they designed this ADC circuit in Cadence Virtuoso, and we taped it out. Eventually, we got a chip, connect all the signal to the ADC, and it didn't work. So we learned a lot of lessons from that design, and I'm thinking we should really do that again. So I found out some minor issues with the ADC design on the timing part, and I fixed it a few days ago. Regarding this timing, okay, so on Wednesday, so today we're going to talk about the timing, and Wednesday there will be a quiz on the timing. So after today's lecture, study it, okay, super important. And all the other part of the circuit, and this is a new diagram I just ran over the weekend. And disregard all the simulation glitches. These spikes doesn't mean anything. So when you do a low pass filter, and eventually these won't really show up. So you can see the sine wave is a black line. You couldn't see. If you zoom in, you can see the black line over here. That's the sine wave. It's a perfect simulation curve, and the ADC is trying to digitize it. It's an 8-bit ADC, so you can tell the resolution is not perfect, but it is able to follow that sine wave and digitize it. You can see all these little steps. It's trying to do the SAR algorithm, right? Trying to convert it. So I think the design is almost 95%, and the only thing I still want to change is the comparator circuit. This one works, but there's a better option after doing a literature study. So I found out we probably can do a better job on this one, but for the rest of the circuit, it's really straightforward. We can directly use. Okay, so eventually, my goal, since I'm trying to not lecture too much after spring break, so we have like 5 to 6 weeks to work on it, including the lab times and also the lecture times. So the goal is to build this 8-bit ADC in schematic and layout in Cadence. Hopefully, if not, we can still do everything in electro VLSI, right? As a worst case. All right, now let's look at the timing. Okay. So timing means when this circuit is gonna do what, right? You must be very familiar with this structure. It's push and pull, right? And you need a transistor here as a switch to pass VDD to the cap here. And this one receives the gate voltage from the boosted voltage of this point. And then you need a switch, okay, to pull and push. And starting from this point, because this capacitor is going to hold that floating VDD, right? So apparently you need a little PMOS as a switch. And here is another inverter. And the signal phase is phi. This is phi naught. Let's make it. Okay? And you need another 2 switches and connect to the reservoir, let's say 100 picofarads. And here we need 2 switches and short to ground. And we use these 2 transistors to reset the sample and hold circuit. Okay, and this is always on. This guy's always on. So the reason for that is this is trying to protect, because you got relatively higher voltage over here, higher than VDD. So this one is trying to protect this transistor. So making this a little bit white, but it's always on, right? And we got these 2, and this is a signal. And there's another NMOS transistor is shorted here, and the drain is receiving this voltage and go to the gate. And the gate here shares the same gate as these transistors. I'm going to tell you why we need this transistor in a bit, right? And we're going to label this one as C3. The reason we label it that way is because it's trying to use the same names as the components being used for the paper, right? I have that paper on my website. Abel's published in 1999. Okay. Same age. Oh, it's even older than you. Is it? So look at these ones, C3, and this is IMA, IM13. So M is MOSFET, okay? So this is M13. This is VDD. This little NMOS here is M5. And this joint here is B. Let's label it as, A. Here's A. Here's B. Here's C. And this one directly goes down here. Okay, so that's the sample and hold circuit we're going to use. So, first point, when phi naught is 1, what's going to happen? When phi naught is 1, no clue at all? Always think about this simulation diagram here. Look at this one. Sample, track is following this black line and then hold. This pulse is probably inverted. Okay, I'm just trying to show a rising edge, but the thing is, for the sample and hold circuit, for the D flip-flop over here, sorry, not D flip-flop, the sample and hold circuit over here, this guy, I can tell that this clock is getting inverted. So when I'm talking about the phi naught, it's actually the signal line over here, right? Because I don't have an inverter as this point. So just looking at this diagram, that's good enough. Because you can see phi naught, they are the same signal line. Okay, if this is 1, definitely this transistor is on. And you always think about, hey, this is the ground. Whenever this is on, which means I'm passing a 0, and this transistor is always on because it's shorted to VDD, so it's always on. So in that case, NMOS is very good at passing 0, so 0 is going to be passed to point C. If C is getting 0, all these NMOSs are off. Okay, so whatever your signal voltage is, it won't pass. So none of these transistors will pass the VS to the capacitor. So it's basically holding the previous state. It's holding. Or you can say when it's holding, it's trying to reset whatever charge is being previously stored at the gate. So it's holding the voltage over here. You can imagine it's a long straight line, a flat line in your diagrams holding it. So during this period, you have the time to do the ADC conversion. Very important, okay? And also during the same time, because the seventh hole is not working anymore. It's just holding. And your ADC, the downstream circuits like the SAR blocks are working really, really hard to do all the 9 cycles of conversions. And so in that case, you do have the time to reset everything. It's passing the 0 here. So previously, whatever stored over here, the charges across the gate will be reset by the 0, will be discharged to the 0. Or you can say the 0 is going to reset all the voltages of the gate. So when phi naught is 1, what's happening? It's resetting and it's holding, right? The second point, keep in mind, it will be on quiz on Wednesday, okay? When this is 0, what's going to happen? When phi naught is 0, what's going to happen? When phi naught 0 is doing, so this is off. This is off. So look at this. When this is 0, so before it jumps to 0, it was 1, right? So when this signal line is 1, this is on. So when this is on, it's pulling, right? It's pulling. Remember, this is always high voltage, and this voltage is higher than VDD. So in that case, when this is pulling, this NMOS is able to be widely open. It's widely open, and it is able to pass the entire VDD to the cap. So eventually, C3 is gonna be fully charged to VDD, and that will be a floating VDD once you turn this gate off. So eventually, it becomes a floating VDD, has a finite amount of charges being stored across the 2 plates, because when this becomes 0, this is off. All right, nothing is going to discharge it. It's going to be a floating VDD, floating VDD. All right, so whenever this is the 1, it pulls VDD here, and then whenever this is 0, it turns it off and this guy becomes a floating VDD. All right, so now when this is 0, it's a floating VDD. First, second, it's doing sample and track. Because the signal over here is able to, remember, it's like another voltage source, Because this is 0, phi naught is 0, so phi is 1. So which means this guy is 1. If this guy is 1, NMOS over here, the little NMOS here is on. And B is 0. Agree with that? It's very simple, right? If this is 0, this is 1. If this is 1, it's the input of the inverter, and output of the inverter is going to be 0. Okay? Everyone knows that. And so B is 0. If B is 0, the gate of the PMOS is 0. And imagine that it's basically forming a short circuit. If you're looking at the top of the plate of the VDD, the top of the capacitor, and then you can see this wire is being shorted to this point through this NMOS because the NMOS is on, right? So it's forming a short circuit to B. So it's basically it's applying VDD across VSG. Do you agree with that? Phi is on, NMOS is on. This wire here, A, so A and B is basically, VDD is basically added to the VSG of the PMOS because this wire is shorted to the output of the inverter, which is being put down to this line, and this line is added to the bottom plate of the cap. So the cap is storing a plus VDD, one VDD over here across it. So eventually, this one VDD is applied to the VSG of the PMOS. So the PMOS is on. Okay? If the PMOS is on, it's able to pass at least the VDD to this point. So C is VDD. Now, it's like a floating VDD is being applied to the VSG of the PMOS to turn it on. Over here. So what's happening is now you already have a VDD being added to it, and now it's trying to push this VS to that DC voltage VDD. How? Because we already know that this one is VDD now at least, and this is turning on this guy, this NMOS, and also this NMOS. But now let's just look at this NMOS. Because this NMOS is on, so the signal, the analog voltage, is able to pass, okay, to the same point. You can see it's still the same point. It's the bottom plate of the cap. So basically, remember what we learned in the charge pump, and also did the quiz on Friday last week, right? It is able to push. It's able to add this VS to this VDD. Eventually, it's adding this VS to VDD. So eventually, the voltage here is labeled as D. So when phi is 1, A shorted to B, and VDD across C3 is applied to VSG of MA. So MA is on. And VS, so the signal here is VS. VS got pushed into C3. Okay, so VC3 eventually equals what? Equals VSG of MA, and that equals VDD plus VS minus VS, which is VDD. And now let's see if that is true. All right, so VC3 is over here, is applied to here, and because VS is able to arrive here and go through the NMOS and arrive at B, eventually here the gate voltage is VS, because that's just the one wire. And also VS is pushing into the capacitor, so eventually the voltage here becomes VS plus VDD as well, okay, which is the voltage at this point, because this is VDD and add VS to ground, so the voltage at this point is VDD plus VS. And because VS arrives at this point, so eventually VSG is VDD plus VS minus VS, and which is eventually VDD. So you are getting a constant VDD across the PMOS, which is good. Okay, and because the voltage at this point is VDD plus VS, okay, so the entire VDD plus VS can reach here. Can reach here. And keep in mind, this is the same line, okay? And this is the VS. So VGS equals VDD plus VS minus VS as well, which is VDD. And that's the whole point of the circuit, trying to make the VGS constant for this sampling transistor. Okay, there will be a couple of more important points over here. And that's the next one is, why do we need M13? Why do we need M13? So the voltage here to turn on this PMOS is not a high voltage. It's original 0 to 5 volts logic. It's the regular VDD to 0. Okay? So just in case if the signal over here is larger than VDD minus VTHN, this NMOS will be off, which is bad. So you need a NMOS transistor has a higher voltage of the gate in order to pass, no matter what signal available over here. Definitely, this signal will not be larger than VDD because that's the range of the ADC. Nobody want to do that. Nobody will do that. It's not allowed. Okay, but it could be larger than VDD minus VTHN, and in that case, this NMOS will be off because this voltage to turn on this NMOS is just a VDD. All right, it's too low. However, you need another transistor over here because this one's gate is shorted to this special point, which is VDD plus VS. So in that case, this will be able to pass the entire voltage over here to B. Okay? And in that case, just in case this transistor is off, so this will be still on to pass everything to B. So the point to have M13 is when VS exceeds VDD minus VTHN. Usually we don't do that. You know, the analog signal is usually pretty small, again a few hundred millivolts. But just in case you want to sample a pretty large voltage, and in that case the M5, which is this transistor M5, will be off. So adding M13 there will be helpful. Can keep VG of M8 BVS in this situation. So now we know that at least when phi naught is 0, it's doing sample and track. When phi naught is 1, it's pulling and it's doing hold. Okay, so study this, all the different points, or the key points over here, and look at the circuit, trying to draw the circuit diagram by yourself without looking at it. And hopefully I can prepare for the quiz on Wednesday. And some other key points over here, because this guy is driving, I think this is a different circuit, so we don't have to worry about that, really. Okay, so this PMOS is in its own well. For the sizing of these parts, it's not really critical, so I think we are fine. All right, that's it. So we know the timing for phi. Okay, so when phi is 1, doing what? When phi is 0, doing what? So if you want to have this one work with your SAR block, I won't be able to draw like 9 of different flops. Let's just do 5. This is going to 4-bit ADC. What's the name of the first row? What's the name of the circuit in the first row? Sequencer, right? It's just shifting the ones to the right and adding 0 to the MSB. Sequencer. So you ground the first D because eventually after reset everything, when you're passing 1 to the right and you're adding 0 to the front. So that's why you're grounding the first one. So you want to pass, you want to shift the 0 to the right, or adding to the left hand side of the 1. And there's a set and reset, and it's a active low, keep in mind. So set is setting the first one and resetting the following ones. So you're getting a 1 and zeros as an initial state of the ADC conversion. Okay? So you need a clock cycle. You need a 1 clock cycle doing the reset. So which means you need the zero pulse, a dip over here to reset it. So the first one becomes 1, all the following ones become 0. Just the 1 dip, 1 clock cycle at the very beginning of each conversion. And definitely it's a serial in, parallel out. So all the Q's need to be shorted to the D's of the next stage. Okay, and you need a Q naught. I'm going to explain you why. Why we need a Q naught over here specifically. And you need a clock. And this clock can be fast. That's going to be the main clock of the SAR block. Okay, so when you are running the timing for this one, you can just think about it in your mind. So you need a dip here first. Give a dip. So this one is getting set, and all the following ones are getting reset. So it's forming a 1 and all zeros. Same for these ones. Why have a bar on the top of the set and reset? Why is low active? Or active low, I'm sorry. Remember the TI D flip-flop you guys simulated for the homework assignment? Right? Set and reset is neither 0 to set and reset, right? So that's why it's active low. And remember the comparator's output is being fed into all the D's, but not the last one. The last one is just 1, 2, 3, 4. So the last one doesn't matter because it's not a data flip-flop being used as data. It's just providing a clock for the previous stage. So let's think about one key point over here. So whenever I'm setting, I'm getting 1 zeros. Okay. And these guys also need to set and reset as well. Need to be set as well because it's trying to pass that 1 here, so it's able to set it. But the thing is, this is also active low. So you cannot use the 1 to set it. What's the solution for that? Yes, I'm forming 1 and zeros at Q. Okay? However, this guy needs a 0 to set. What I can do? Use Q naught. Use Q naught. Important. All right. And then if this is the 1, Q naught becomes 0. So you are basically getting 0, 1, 1, 1, 1. So the 1 is not doing anything because it's active low, but 0 is gonna set it. Okay. So you are getting a 1 and zeros. So you can start the conversion. And the Q of the next stage is used as a clock from the previous stage. So this one doesn't matter, you can ground it. It's okay. So this one is just receiving a Q naught signal to set everything and then provide a resting edge for this stage, for this stage over here in front of it. Okay, so in that case, you can imagine you'll need a dip here. You'll need a dip here to do the generate the initial state. And after that dip, you will be able to start a conversion right away. However, this dip has to happen after this dip. Why? So before do the conversion, you need 2 dips. Here, these are the data outputs. 4 bits. This is, so these are the comparative output, okay? Remember, A3, A2, A1, A0, these are the comparative output. And after this, you need another 4-bit D flip-flop with a clock. We can call it, I call it clock door. It's like a door, right? We can kick out all the output. So it's parallel in, parallel out. So whenever, because you are having a lot of intermediate values over here, which are not the final results. During the conversion, remember you have, for the 8-bit ADC, you have like 9 intermediate states, and these are not final results. So these ones, all these ones are being shifted, so the results are changing. And eventually, you know that you got a final results ready, you just kick it out to the output. So this is the final output. So there will be a rising edge here. Why is the rising edge? Because we are using the same D flip-flops, and that D flip-flop is the rising edge D flip-flop. It's the rising edge. Whenever the rising edge arrives, you just need a one little pulse to make it happen. So you can imagine if this is an 8-bit ADC, you need 9 different states, and you need 2 dips. You need 2 dips in front of it to set it up. So eventually, there are a lot of things to consider. Okay, you need to wait. But how many cycles? So here's a clock of the SAR ADC. It's called clock. The SAR block, okay? It's gonna be a miserable job. I'm gonna draw like 20 rising edges. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hopefully that's enough. Phi naught. What is phi naught? Phi naught is a signal over here. I pull it down, I'm doing what? If I pull it down here, I told you it's a dip, okay? So previously it was 1, and I pull it down from 1, pull it down to 0 from 1. What's gonna happen? I don't know if you have that feeling. I mean, for circuit analysis, you should always have your neurons of your brain have a connection with the circuits, so you can feel it. Like an avatar, you are making a connection to something, right? So whenever this one being put down, you feel like yourself is dropping, like when you are sleeping and dreaming, drop from the building or something like that. You feel something's dropping. What is dropping? The water hanging on the top. A bucket of water is going to dump the entire bucket of water down to the cap. It's dropping, like pulling, because whenever this one is pulling down to 0, so when it's pulling up, it's dropping, right? When it's pulling down, shut it off, and then this one is getting an isolated, a floating VDD stored at the cap. Okay, so in that case, when this one is down, this is down, right? So it's doing what? It's doing sample and track, because it's not resetting. Okay, because this is down, so it's not resetting. If it's not resetting, which means it's sample and tracking. So it's sample and tracking. So the signal is be able to pass to this point and start tracking, because everything can go through. It's doing this. All right. And when this is off, this guy's off, it starts holding, right? So now let's show the dip first. If we label this one as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are all the little rising edges. So the rising edge is going to update everything. Rising edges. So let's start the dip at the first one. Keep in mind that it's only updating at the rising edge because that's the original clock. So eventually, it only able to make some changes to the state of the pulse at the rising edge. If there's no rising edge, nothing can happen. Keep in mind. Similar to the for people embedded, you'll learn from Verilog, right? So it's always at the rising edge. The rising edge is gonna update everything. Okay, do this first. And then the SAR, set and reset clock, which is this guy here. When should you make a dip here? Think about this phi. Ground. If it's ground, it's doing 7-point track. Okay? It pulls it up. It's doing what? There are only two options, really. Here, seven-point track. What about here? Starting what? Hold. Come on, only two options. You could even just guess, right? Okay, so we start holding, which means the DC voltage is available. The DC voltage is available. So the value is ready provided to the SAR ADC. You are ready to do the conversion. But before you do the conversion, what's the first thing you need to do? What is the first thing you need to do? Generate the first state. What's the first state? 1, all zeros. 1 and all the trailing zeros. So in that case, you need to do a dip here, do a reset. It's a set for the first one, but just reset for all the following ones to generate that 100 state. Remember that ADC's algorithm, the first little circle is 1 and all zeros, right? You don't want to do it here because it's not ready yet. And whenever you generate that state, you want this DC value available. This DC value available because this is the DC voltage. Remember that diagram? There's no lock, there's no latch in between these two circuits. So whenever this is getting that analog voltage output over here, it will go through everything. There's no clock controlling it. There's nothing controlling this guy. So whenever the voltage appears here, it starts doing the conversion. It's comparing, right? Nothing can control it. That is why you need this one to be held here first. So you get a good voltage value or the voltage value you want to convert. Here ready first, to hold it first, and then make a dip here to start a conversion. Otherwise, the first cycle you are converting the different voltage. For example, if you don't wait it until that point, so you are the first conversion, you are converting the voltage here, and the second is probably moving to here. It's generating errors. So that is why you want to keep it constant. Having this one ready first. Hold it first, then do the dip. So apparently you want this dip happen at here. And one more time, this one doesn't update until the rising edge. So it's going to look like this. All right, now we can start counting. And you got another clock. It's called clock and door. It's a door clock. because this one's clock, because now the conversion starts. Once it enters, or once this one have the falling edge, it forms that 110 state, right? So 100s, and that 100s digital data will be converted to analog voltage by the DAC, and it will directly fed back to the inverting terminal of the comparator, and it's already started conversion. So during this period, it's trying to generate A7 if it's the 8-bit ADC. So in that case, as this rising edge, A7 will be latched into the code register. This rising edge, A7 is ready, is latched. So it could be on the quiz, okay? So I'm asking, at this rising edge, what is the code over here? Showing up over here. What is the code? Let's see if anyone can answer that. Probably not. When A7 is available, what is the code over here? Is that true? That one was a one got set or reset at the very beginning. So whenever you plug A7 in here, I'm having a 4-bit, but just imagine this is a 8-bit. So A7 will be plugging over here. So the previous one, will be shifted to the right. So we're getting A7, 1, and O zeros. So in that case, the following rising edge is going to give you A6 will be latched into the code over here. Where's the door? How do we draw the door? We don't have the time to run the quiz today, so that'll be on Wednesday. So what about the door? How to connect the door to it? The final result doesn't seem to have an output out here. So this is the analog input. So where's the digital output? It's over here. Over here. Whenever it's ready, there's a latch, right? There's a clock. This will be D3, D2, D1, D0. Yeah, these ones they do have some intermediate results, but eventually, whenever the final result is ready, you have a rising edge of the clock, you kick it out. So this is the final output. Okay, now let's come back here. A6, A5 will be latched to here. A4, A3, A2, A1, A0 done. You don't need no more. So once A0 is being latched into the result here, you have all the results from A7 to A0. Okay? Since you are using the same clock, should you just kick it out using this rising edge, or you want to wait for another cycle? So like I'm doing the rising edge, so these rising edges, right? A7 is available, A6 is available, A5 is available, A0 is available. So should I just kick it out at the same time when A0 is available to make it fast? So it's like when you are sending it out, A0 is not really ready yet. Okay, it's the same time when A0 is ready, you kick it out. Who knows which one get there first? It might be a 1, you know, the 1 is not being shifted out yet, so you are still getting the old 1 over here. So what you want to do is wait for another cycle. So after this cycle, all the A7s through A0s are available and ready, sitting here, and you wait for another cycle until this point, until this clock cycle, you kick it out. So eventually this one will be the rising edge of the clock, of the clock door rising edge. And the same thing, it only updates at the rising edge, so it has to pull it down until here. What's next? All this happens by a counter because I count by how many cycles I have, and that counter is able to reset the counter to 0, so it starts counting from 0 again. So from here, it's count 1. Whenever it counts 1, it pull it down and go up. Because after 1, the next cycle is not 1 anymore. I'm going to show the circuit of the counter really quick. It's really easy. That's the easier part of it. So we just request the signal first, and then we know how we can design a circuit to implement it. And then the same thing. So for this one, I need a rising edge counted at 2. So the counter counts at 2, and then we make a dip. And this one, it count to 11, and we make a rising edge. So this is pretty simple. All these could all be rising edges, which is inverted. So eventually inverted. That's pretty simple. And now, after this one, after this clock is done, so we need to count to 11 to make a rising edge here, right? So after that clock, the final output is being kicked out to here, being latched to the output. So we get a first analog data point converted. Okay, so we don't have to worry about that anymore since it's already latched over here. It's already latched over here. So we can, and also the clock can see the clock become 0. So it's a memory. It's the memory. So we don't have to worry about that. So nothing can be changed. So it's just waiting for anything externally to sample it, to take it out, like parallel input or something, or serial like SPI or UART. You can short all these into a serial in parallel in, serial out. No matter what. So the mission of the ADC is done. So eventually, after this one, you can start a new. You can reset the counter, so it's able to count from 0 and to 1 to 11 again. So you want to reset it. So we need a reset signal for the counter. This guy, reset it. So at the falling edge of the reset, what can I do? Because here, at the rising edge, the counter will be reset to 0. The counter starts counting from zeros. And after this point, the counter is already reset. So in that case, let me ask you a question. Here, counter becomes 0, outputs. So here, counter is counting what? Counter is counting 0 here. Counter is counting what here? 1. Look at this. Happy ending. Start another cycle. Makes sense? What is a counter? Counter is something we don't have to worry about because it's just so simple, right? Design a counter circuit is really simple. Look at this one. It's just a D flip-flop. Use the same D flip-flop and feed in your Q naught to D. Just short these two wires, and it's able to divide the frequency by 2. So eventually 4 megahertz will give you a 2 megahertz output over here. That's how that works, okay? Just keep doing that. I can run the simulation on Wednesday. So this is a 4-bit counter. I have a 2 megahertz input, right? And eventually these outputs are going to do a counting, starting from, so the counting is based on this clock cycle. The rising edge is going to count by 1. And you can see all these D flip-flops, they have setting and resetting the same D flip-flop as we simulated in the homework assignment. So whenever you receive the 0, it's resetting everything. So it's, all the outputs shows the 0 as this from Q3, Q4, Q3, Q2, Q1. And for the counter output, okay, if you look at this one, it is counting to 1. You can see Q4 to Q1 is 0, 0, 0, 1, because that's the only combination of the logic can make you a 1 here. This is the NAND gate. I mean, NAND gate and inverter is forming actually an AND gate. I can directly just use the AND gate, right? So that's the only combination of the numbers can give you a 1 as the output. So that 1 will form a rising edge. Will form a rising edge for this purpose. I are saying this is a falling edge, so it's just inverted. It's just inverted. Okay, you can just invert it. So now let me take a look. So this is counting to 1. This is inverted by twice. So I think this probably is wrong here. Yeah, I think I used the wrong circuit. So this should be just a NAND gate because it's getting inverted. It shouldn't invert it twice. Invert twice is going to give you a rising edge. So it becomes a rising edge instead of falling edge. We'll look into details of this circuit on Wednesday, okay? We'll do a review on this on Wednesday as well, and by the end of the lecture on Wednesday, we'll do the quiz on, still the quiz on the charge pumps. Okay, so the quiz on this will be on Friday, right? Study this circuit, the timing diagram over here.